I will present a fast and effective parameterization of water quality models. As you know, parameter estimation is an important part of modeling. When you change the model parameters, the model output values are also changed. However, parameter estimation of water quality models is not a straightforward task because in water quality models typically characterized by a high number of parameters, variable, and line calculation time. Furthermore, only few reliable calibration data is available for the water quality models. So the objective of this research is to present a solution to the parameterization of water quality model by the use of fast global sensitivity analysis to identify the influential parameters and then using the manual calibration. The success of parameterization and the identifiability of the parameters are evaluated using Bayesian uncertainty assessment. Using the uncertainty analysis, it's possible to quantify the parameter and the simulation uncertainty. So in the following, I will present the method and materials and next result and finally the conclusions. As a simulation tool, the conceptual integrated tool for water quality assessment is selected. This tool has been developed at VUB as an alternative tool to detailed water quality simulators. The case study is the River Dender in Belgium, and the interested water quality variables are dissolved oxygen, biological oxygen demand, nitrate, and ammonia. Prior to calibration, global sensitivity analysis is performed to identify the influential parameters. Many different global sensitivity analysis has been developed, from simple methods to advanced quantitative ones. Latin hypercube one factor at time is an example of a screening method which is fast and simple, requiring limited number of model evaluations. But this method is not reliable for nonlinear systems. POAN is an example of moment-independent method, which is advanced method and reliable for nonlinear systems, but it needs a high number of model evaluations. As an automatic calibration and uncertainty analysis algorithm, DREAM method is selected. Before calibration, we consider uniform distribution for the feasible parameter range. Using the observation with the measurement, the DREAM algorithm identified the optimum range for the parameter and the posterior distribution for the parameter. Then using the posterior distribution for the parameters, we run the model and then we can have a uncertainty range for the simulation due to the parameter uncertainty. But we see that some points, some measurements are not covered by the uncertainty range. So it indicates that other source of uncertainty should be considered. By analyzing the residual, we can have a total uncertainty range covering almost all the measurements. The uncertainty analysis require a high number of model evaluation. Thanks to the fast simulation time of the conceptual model, it's possible to perform DREAM. As I mentioned, Latin hypercube one factor at time is computationally efficient and fast. But the question is that, is it reliable? So we try to test it. To perform the Latin hypercube one factor at time method for the conceptual model, we select 10 parameters and 20 samples, 200 samples. So the total number of model evaluations is 2,200. As a model output, mean absolute error is selected. So to evaluate the result of the Latin hypercube one factor at time, we perform point for the conceptual water quality model. In addition to the 10 parameters, we also calculate the sensitivity index of a dummy parameter as a threshold for the screening. The number of samples is set to 300. So the total model number of evaluation is almost 33,000. So it's 50 times more than that for the latent hypercube one factor at time method. And as an model output, mean absolute error is selected. So as the calibration data is very limited, it's monthly data, so the manual calibration is performed based on visual evaluation. The DREAM algorithm is performed for the calibration period, and the interested variables are dissolved oxygen and biological oxygen demand. Considering the result of the sensitivity analysis, three most influential parameters for these two water quality variables are selected, and the total number of model evaluations is set to 12,000. So this figure shows the result of the sensitivity analysis for the Latin hypercube one factor at time method for the dissolved oxygen. So these four parameters are selected as influential. To evaluate the Latin hypercube one factor at time method, we see the result of the point for dissolved oxygen. Considering the sensitivity index of the dummy parameter, these four parameters are selected as influential. So we see that the Latin hypercube one factor at time provides the parameter ranking very similar to those of point. So this figure shows the result of the dissolved oxygen for the calibration and validation period. During the calibration, we see that the trend is simulated perfectly, but we have two points that is underestimation. These points are related to the uh, summer, and maybe the reason is the algae that is not simulated in the model. During the validation period, the result is acceptable. This figure shows the result for BOD. We see that the trend is simulated acceptable and satisfactory during the calibration and validation period. The result for nitrate is almost perfect, and the trend is simulated very well. For ammonia, during the calibration, we have an acceptable result, but for the validation is not acceptable. So these figures show the optimum parameter range for the influential parameters identified by DREAM algorithm. We see that the influential parameters are well identified. This figure shows the result of the uncertainty analysis. The black range is the uncertainty range due to the parameter uncertainty, and the gray one is the 95% uncertainty interval due to the total uncertainty. We see that almost 50% of the measurement are covered by the black range, and it means that almost 50% of the total uncertainty is explained by the parameter uncertainty, and the other 50% of the total uncertainty is explained by the other source of uncertainty, such as input uncertainty and model structural uncertainty. So in conclusion, a fast screening method is preferred over an advanced computationally expensive method for the calibration of the and the simulation uncertainty range due to parameters cannot cover the observation, and to explain the total uncertainty, we should consider the other source of uncertainty during the modeling. So thank you for your consideration.
Thank you very much for your presentation. Is any question from the audience?
There is one in the chat. Maybe Emily can ask it herself. Emily?
Yeah.
So maybe I will read the question then. Oh, she can't speak anymore. Okay. It's because you're muted, Emily, but it's okay. On slide 16, on the right figure, it looks like you discarded parameters which indices were slightly higher than the dummy parameter index. Why?
This. Okay, this figure.
I think so, yes.
So I select the top 4 parameters considering the dashed line.
Yeah, I think she actually means that, for example, if you look at the dummy, that it is slightly lower than the dashed line. And then, for example, RS1 is slightly higher, but it's really very small. So I think she asks why yeah.
In fact, in this figure, I don't show the result of the resampling. So if we consider the 95% on the interval for the sensitivity index, then this figure is okay. Bootstrapping, I mean.
Yeah, I know what you mean, of course. So I hope this is clear for you, Emily. So we actually did bootstrapping to get uncertainty bands or confidence intervals for the different values of the parameter indices. And there it showed actually that this line is the reliable one, let's say, to make it short. Are there other questions? I'm taking over, Giorgio, sorry. No other questions?
I have a question regarding the slide that was just removed. How did you select the dash line? Is a sort of cutoff threshold. So which value did you? How do you decide?
The value of the dummy parameter, the sensitivity index of the dummy parameters.
Okay, so it's a result of the application of the methods.
So it's I actually showed this earlier this session, the use of this dummy parameter, and it's this value taking into account also the uncertainty band of this value that is taken as this dashed line as threshold.
And it's obtained by just random sampling. It's not affected by the model.
Mm-hmm.
Yeah.
An important thing maybe to highlight here with this slide, and that's maybe something also something that you said, Giorgio, the order of the parameters is not completely the same, because yeah, actually both the LHOAT and PON are not what we call quantitative methods. You had another definition of quantitative methods, but a screening method like the LHOAT can say which parameters are influential and which are not, but the actual value is not as quantitative as, for example, for the Sobel method. So maybe that's something that should be taken into account also, why the difference in ranking, there's a small difference in ranking which could be related to that.
Okay, thank you.
But that's just the type of definition. You had the definition for quantitative and qualitative based on numbers, but sometimes it's also made based on the fact if for example, for Sobel, it's really the percentage of the contribution to the output variance. So it's a real value, whereas here, the value doesn't say a lot. It's not that it's a sort of percentage of contribution for screening methods.
No, but the higher value means still more sensitive.
Yes.
Less, like the Sobel, it's less specific meaning. It's an average of local sensitivities across the space.
Yeah. Okay, thank you.